So before going on to the next speaker, let me just give you all a brief reminder of the theme of seminar, that is chemistry in the eyes of past and present Vidyamandira student. Our previous speaker is a former student of Vidyamandira, while the one that I'm gonna introduce now is a fellow batchmate of mine. So keeping this in mind, I'll be a bit more informally introducing him. His name is Kanchon Sheikh. After spending nearly 2 years with him in the college, one thing I noticed about him is that he's always hunger stricken. Whenever someone says something to him, he'll be like, one thing that will inevitably come from his mouth is like, bhai khawa. I really used to wonder, like, how can a human being be always so much hungry? But keeping aside all the joke, Kanchun is one of the brightest of our batch. Not only in studies, he has also proved his mettle in drawing by being an active participant in Inter-Bhavan magazine competition and winning allocates for our Bhavan. So before coming to Vidyamandira, he did his schooling from Hans Pukuria Vidyapith and passed the board exams with flying colors. He is currently doing a reading project under the guidance of Dr. Piyush Shashmal from JNU. His research interests include bio-inspired catalysts, coordination complexes, and drug designing. But today, he will be giving his talk on color chemistry. So I would now request Kanchun to proceed with his speech. Off to you, Kanchun.
Thank you, Anirban. Am I audible properly?
Yes, you are.
Absolutely, absolutely.
হ্যাঁ বাড়া রাত্রিবেলা মাঝে মাঝে ভয় হচ্ছিল।
So good morning everyone and good evening. The title of my talk, as you can see, is the chemistry of colors and its beauty. This talk will be for someone a revisionary lecture. For someone it will be a bit hard to understand, and for someone it will be something new to study. But hope you all will enjoy it. As we all belong to the chemistry family, we have already entered into the laboratories, especially inorganic chemistry laboratories. Brothers of the first years, who I hope they also entered in the school laboratories, where you have seen these compounds. First one is nickel chloride, second one is copper sulfate, third one is K2CH27 potassium dichromate, then potassium chromate, K3FeCN6, and this is nickel DMG color. Now the interesting feature about this is the color about all complexes. How the color arises and why we কেন আমরা color দেখি, why we observe these colors. This is very much interesting. At first we should know what is color. Color, this is especially a part of electromagnetic radiation which looks something like this, and within this visible region we human eye perceive these colors. Now we should know how the color arises. What is the origin of the color? If we consider two electronic levels of energy E1 and E2, and if there is a particle in the lower energy state, and if radiation is fall upon that, it is excited to the upper energy level, and as energy uncertainty principle says, if energy uncertainty is higher, then the time period will be low. So it must in general it must come down, leaving back a radiation. If this radiation falls in the within the visible region, then we see color. Now what is the color, what color we see, is that that is emitted or that is absorbed? It is actually the color that is emitted. We see the color that is left behind is perceived by our eyes. This is the complementary color cycle. That is, if yellow is absorbed, then we see the color purple, and so on. Now, we specially talk in this lecture about the color of transition metal complexes. Now, how they show colors? The color arises due to two reasons. One is DD transition and second one is charge transfer transition. Now, there are some prerequisites to a transition to take place. That is, we have to have the suitable radiation that matches the two energy gaps.
The second half of the seminar. 3
Hello?
lectures, 1.
Hello?
Yes. Continue.
The prerequisites for a transition to take place is the suitable radiation that matches the two energy gaps. This is the resonance condition. And the second one is we have to have a energy, have to have an electron or electrons in the lower energy level and vacancy in the higher energy level, so that the transition can take place. And third one is some selection rules. These are of two types. One is Laporte selection rule, one is spin selection rule. Laporte selection rule says that the transition between the orbitals that should have this condition that delta L should be plus minus 1. So there won't be any transition for S2S, P2P, D2D, F2F, etc. This is because there is one parameter called transition moment integral, which has the form like this. Now, if the two orbitals are the same, that means they have same symmetry, and the group theoretical terms of them will be 1 and 1, and this the middle one is dipole moment, which has the which is equivalent to a coordinate, that is x, y, or z, that has the group theoretical term symbol -1. So if this transition moment integral is even, then only the transition takes place. If it is odd, then the transition won't take place. If the symmetry of the two orbitals are the same, that is S to S, if we consider, then this will be 1, this will be 1, and middle will be -1. The total product will be -1, that is odd. Then the transition won't take place. The second one is spin selection rule, that says the delta S, that is spin multiplicity change, should be 0. That is, we can have the transition like this lower level to upper level, but we can't have the transition like with an electron in upper level and in lower level, and then we expect a transition from lower level to upper level. That is not allowed. Now, when we speak about transition metal complexes, then the major things that comes to our mind is the d orbitals. The special thing about these complexes, this is the energy splitting of the d orbitals. When the metal ion is free, then the 5 d orbitals are degenerate. When the metal is subjected to a spherical electric field, then all the orbitals equally energetically goes up, and this is called a barycenter. And if we replace the spherical field with the octahedral field of same strength, then we observe that the 3 orbitals energetically goes down and the 2 orbitals energetically goes up. This is because in octahedral geometry, the ligands are in the 6 corners of an octahedron, and we know that dx square minus y square and dz square, these are along the axis, so this will face more repulsion with the field, and thus this goes energetically up. Thus, there are two energy levels, T2G and EG. These are named as, and thus we can expect a transition from T2G level to EG level. but this is not actually allowed. Why so? If this is not allowed, then how do they show color? Because this is not allowed, because D2Z orbital, we name this as D2Z, but this is actually a d orbital, and EG also a d orbital. We group them as two different groups. So how do they show color? There is some relaxation of the rules called Laporte Rule, that is for which this was seemed to be forbidden. Now, how this relaxation is occurred? This is because of the 3 points, 3 reasons. One is DP mixing, that is mixing of d orbital and p orbital of the metal. One is Fibonic coupling, and another is metal ligand covalent bond formation. DP mixing says that DP mixing have to when we consider a mixing, then the orbitals should have same symmetry as we have considered in hybridization. Then sp hybridization can take place, but the orbitals, lobes of the orbital should have same symmetry. Now, for octahedral symmetry, there is center of inversion. This is the p orbitals in octahedral geometry. These are of ungerarded symmetry, because if we pass from one lobe to another lobe through the center of inversion, then their sign changes. The sign of the lobe changes. So these all the p orbitals are ungerarded symmetry, and the d orbitals also looks like the same. For the p orbitals, they are ungerarded, and the d orbitals, they are gerarded. Now, therefore, no p and d mixing will be possible for octahedral geometry. But tetrahedral geometry, there is no symmetry of, there is no center of inversion. Therefore, there will be strong DP mixing. Thus, from here we can conclude this, that the transition for a tetrahedral compound, that will be more prominent for that of the octahedral compound. Now, coming to the second point, that is Fibonic coupling. Now, Fibonic coupling, vibration between electron and vibration between the electronic and vibrational mode. Coupling between the electronic and vibration modes. When we have we know that molecules, they are continuously vibrating, stretching, that all vibrational modes they are going on. If we consider this motion, or this one, then except the first one, the in all other vibrations, the symmetry of the complex is destroyed. Therefore, as if the symmetry is not present, then DP mixing can take place, and also the transition. Now, if we consider the third point, that is metal ligand covalent bond formation, then this point is totally disregarded by the very popular crystal field theory, but this is taken into account in the molecular orbital theory. If, as we know, the molecular orbital formation, this is carbon atom, this is oxygen. When the sigma orbitals overlap, then form a sigma bond, and when the pi orbitals overlap laterally, they form a pi bond. Similarly, when metal orbitals and ligand orbitals form molecular orbitals of the complexes, then also we can have this type of energy levels. These are the metal orbitals, metal d orbitals, metal s orbitals, metal p orbitals.
অর্ডার হয়েছে কিছু? হ্যাঁ, প্রথম দিন তো কাস্টমার এখন মুশকিল আছে। হ্যাঁ,
In the orbitals, one is A1G, E1G, EG, and T1G. Sorry. Then we can have transition between these two levels. If one electron is here, and then we can expect this transition. This is well established by molecular orbital theory. Now, coming to the second point, that is charge transfer transitions. There are four types of charge transfer transitions: ligand to metal, metal to metal, metal to ligand, and ligand to ligand charge transfer transitions. First one is ligand to metal. when we have a complex like this MnO4 minus, if we consider, then manganese is in +7 state, oxygen is in -2 state. That is, oxygen is electronically rich, manganese is deficient. So we can have a transition like this, oxygen to manganese, and this show color, purple color, as we know. Second one is metal to ligand charge transfer. If we consider these two complexes, that is iron orthophenantholene 2+ and iron bipyridine 2+. Here we have metal to ligand charge transfer. Metal is in lower oxidation state, and iron is in there are vacant pi star orbitals in the ligands. So we can expect a transition showing the color. Third one is the intervalent charge transfer. That is, if we have two metals with different oxidation state, one is reducing and another is oxidizing, then we can also have a transition. Fourth one is ligand to ligand charge transfer. There are two examples here. Actually the transition is taken place between the ligand to the metal ligand orbitals, metal ligand molecular orbitals, from the ligand orbital to metal ligand molecular orbitals. These are the ligands. Then as we are considering colors, then we should remember about the intensity. Intensity is determined by Lambert-Beer's law. As we know, this A equal to epsilon CL. The terms carries their actual meaning, that is popular meaning. And intensity order, as we have described, that intensity of charge transfer will be higher, then the dd transition of tetrahedral, then dd transition of octahedral geometry. Now, what will be this intensity ratio? This is really interesting to know about the ratio. That is, this is the ratio. Charge transfer transition is 1000 times more intense than that in a dd transition of octahedral geometry, and the dd transition in tetrahedral geometry is about 100 times stronger than that in a octahedral geometry. Now, as we have already know that why ClO4, that is perchlorate ClO4 minus, is colorless, but MnO4 minus is colored. Why? Because there is no transition in ClO4 minus. Yes, there is transition, but that transition is not placed in the visible region. Thus, our eye can't accept. Our eyes can't perceive this color. That's why it is colorless. Now, if we consider the popular complex copper sulfate, this is blue in color. So, how would be absorption spectrum look like? This is the absorption spectrum. This shows that the complex absorbs color in this region, and thus we see the complementary color in the blue region. Obviously, the color that is absorbed won't be seen to our eyes. The color that is left, that is seen by our eyes. Now, which transition? But if we have known the transition, we have known about the peaks. Which are the peaks? Now we have to know about the peaks. Which transition gives these peaks? To know that, we have to introduce a new thing, that is energy state. We have already studied or will study this. This is very interesting one. This is denoted as term symbols. Term symbol is nothing but that is having a letter and a digit above and a digit at the subscript. The S here, that is, it is expressed as 2J2L plus 1, 2J2S plus 1 LJ. This S is total spin angular momentum, and 2S plus 1, that is spin multiplicity. The S is calculated as, if we have the spin orbital spin quantum number of individual electrons, then if we sum them, then we get a ms value. The ms as we know, ml, small ml, that contains the values from plus L to minus L. This is also contains the values from minus S to plus S, including 0, with unit difference. The L is total orbital angular momentum. This is also expressed as L. This is expressed as L, and if we get it at sum over ml, if L can have different values. If L is 0, then the symbol will be S. If 1, then we use P. If 2, then use D. If 3, then use F. Now this J, this is total angular momentum, that is spin plus orbital when they couples with each other. Then we have the J levels. Then this J can have values from L minus S to L plus S. For ground state, we should have to consider the Hund's rule. That is S2S plus 1 have to be maximum, 2L plus 1 have to be maximum, and J for less than half field configuration it will be L minus S, and for more than half field configuration this will be L plus S. Now if we consider the D4 atom, then it have D4 atom or ion, then it have this configuration. Then the L value will be plus 2. This is for D orbital, this is having the plus 2 ml value, this is plus 1, this is 0, this is minus 1, this is minus 2. So ml will have the value, L will have the value 2. So 2 stands for D. Now if we calculate capital S, then if there are 4 ampere electrons, then we have the spin or quantum number same for them. That is, if we take plus 2 plus up, then the total spin angular momentum will be 2. So as it is less than half field, the J value will have L minus S, that is 2 minus 2 equal to 0. So the term will be 2S plus 1 will be 5D0. This is the term 5D0. Now the greater contribution in this topic is from Professor Orgel. Professor L.E. Orgel. He let us introduce to Orgel diagram. This is a correlation diagram of the different energy states of a complex. The complexes are assumed to be in high spin state, because for low spin state this diagram is not valid. There are splitting. We should consider here the splitting of Russell-Sanders terms in octahedral and tetrahedral field. We can have terms for each energy level, for each configuration. Then when they are placed in octahedral and tetrahedral field, as we have seen earlier, that the orbitals are orbital energy levels, that is orbital degeneracies, are splitted, are destroyed, and new set of orbitals are formed. This is the Russell-Sanders terms. If the spectroscopy term is S, then the number of states will be 1. Molecular term symbol will be A. If the term is P, then number of states will be 3. Term will be T1. And for D and for F, there is also. We are specially interested in the term D, EG and T2G. This we have known. Now, if we consider the spectra of D1 systems, the D1 system means if there is one electron or one hole. If that is the configuration D1, D9, D4, D6, these all are one system, because D1 has this configuration with one electron, D4 has 4 electrons, but we can consider it as one whole system because one orbital is vacant here. If we consider D9, then also we have total 9 electrons, 5 are in the same spin and 4 are in the opposite spin. So if we consider the opposite spin electrons, then we can say that the 5th orbital is vacant. So this is also one system. For D6 also, there are 6 electrons with 5 in same spin and 1 is in another spin. So if we consider another spin electron, then the system becomes of one system. So for one system, the L will be 2 value. For all of these systems, the capital L will have 2 value. Capital 2s plus 1 will have 2 or 5 values. Which will have 2 values? These two will have 2 values. These two will have value 2 and these two will have value 5. Now for D1, if we consider the D1 system, that is this have term, D1 system has a term 2D, just neglect the J values. So this is the D1 system. When it is applied in crystal field, say in octahedral field, then it splits into two levels, T2G and EG. And when the electron are placed in the splitted orbitals, then it will definitely take place in the T2G level. And the energy gained with respect to this barycenter is defined as the crystal field stabilization energy. That is here minus 4 dq. This is having energy minus 6. Well, sorry, this is having energy plus 6. This is having energy minus 4. The unit in the unit in dq. So when energy radiates, when energy falls on this lower energy level, there will be a transition from lower to higher energy level, and this will go up. The energy will go up. Now for one electron systems, it can be proved that the state of the system is that in which the last electron, that is the unpaired electron, and or the hole resides. So here we have considered one electron system. So there the term will be determined as the electron. So in the orbital, the electron is placed. Here the electron is placed in T2G orbital, so that this configuration have the term T2G, and as one electron is present, thus we have total spin multiplicity equal to 2. For this we will have T2EG. So thus we can generate the two levels. The two levels are generated, and this energy difference is 10 dq. This is del O value. This is similar with 10 dq. Now for different complexes, this value is different. For different complexes, this the x-axis has different point to denote them. If that is in this energy level, so this must need lower energy to excite the electron from lower energy level to higher energy level. And if it is in higher energy, if del O is in the far away in the x-axis, then that will need higher energy to promote the electron from lower energy level to higher energy level. If we consider the examples, there are TiCl6 titanium complex, titanium 3 plus complex, that is titanium has titanium 1 has 1 d electron only. Titanium 3 plus has 1 d electron. So if we consider these complexes, then according to spectrochemical series, we know that the strength of the ligands falls in this order as I have written. So 10 dq value, as the strength of the ligand increases, the 10 dq value also increases. So this is having, we expect, as I have said, that we expect that all the complexes will have different type of energy difference between the T2J and EJ orbitals. So the needed, the applied energy, applied light will have different energies. That is the complexes will absorb in different wavelengths or different frequencies. So if we see the transition frequencies, this is having 13,000, this is 18,900, this is that is the 22,300 for titanium CN6 3 minus complex. Thus that is it is evident that energy gap changes for different complexes and with different ligands. Now this is the titanium 1 absorption spectrum, looks like titanium water aqua complex. This is measured in kilokaiser unit. So this is having 2 peaks actually, but we have seen there is only 2 levels between in the titanium in the one system. But how we can expect two lines from these two levels. There is only possibility of one line. So why this peak is coming here? This hump is coming here. It is, if we draw it simply for our understanding, then this should be the according to our concept, this should be the spectrum should look like, but this looks like this with a hump. We can consider this as two spectrums merged with each other. This is theoretical one, this is practical one. So what can we have to do here? As we have said earlier, some distortion of the complexes can occur. So distortion must have something to play here. So this, if we consider the octahedral complex here, so if the ligands along the z-axis comes towards the comes towards the metal, then the metal ligand bond distance along the z-axis will be lower than that along the x and y axes. And if that goes out from the metal, then the metal ligand bond distance will increase and compared to the x and y axes. Now, if we if the crystal field theory is based on the interaction of metal orbitals with ligands. If the ligands along the z-axis are more closer towards the metal, then the orbitals that have z components will have higher energies, and that along the x and y axes that will have lower energy. So x and y axis, that is xy, that orbital will have the lowest energy, then xz and yz, then x square minus y square, and dz square will have higher energy. But if you say that dx square minus y square, it is along the xy plane, so it have to have lower energy. But this is not true, because as there are 4 ligands along the x and y axes, this will have to have interact with the metal orbitals, leading to increase in energy. So this is referred to as Ian-Taylor distortion. Ian-Taylor distortion, and the energy level that is generated, the energy gap here, that is 2/3 del 2, and the upper one, that is 1/3 del 2, and here the splitting energy of EG levels, they are half del 1 and half del 1. Each is having half del 1 values. So if we consider the Z out distortion also, then what happens? The Z ligands are far away from the metal. So the Z orbital, dz square orbital, will face lower repulsion, so having the lower energy. And this is the splitting pattern in Z in and Z out distorted octahedral geometry. This is referred as Ian-Taylor distortion. It is seen that Ian-Taylor distortion is very much strong in D4 high spin complexes, and D7 low spin complexes, and D9 high spin complexes. D9 complexes. If there are electrons, Ian-Taylor theorem says, if there are electrons, if there are degenerate orbitals and they are unevenly populated, then the system will undergo distortion in such that the total energy of the system is lowered and the degeneracy is lost. If there are one electron, then there is two possibilities. Then the electron can go in this side or this side. That is, Z in distortion may occur or Z out distortion may occur. But if Z in distortion occurs, then the electron is stabilized by 2/3 del 2 amount of energy. But if it undergoes Z out distortion, then it will gain the stability of 1/3 del 2 energy. So it must undergo with higher stabilization. So for D1 complexes, we expect Z in distortion to be occurred. So there is symmetry and naming of the orbitals. For degenerate orbitals, we use the term A or B. For non-degenerate orbitals, for doubly degenerate orbitals, we use the term E. For triply degenerate orbitals, we use T. But when we use A or when we use B, if we rotate the orbital along the principal axis by 90 degree, then two cases may occur. That is, the sign of the lobes of the orbitals can change or not change, or may not change. Here the principal axis in octahedral geometry, if we consider as Z axis, then if the sign changes, if the sign don't change, it is expressed as A. If the sign changes, then it is expressed as B. So these are the orbitals in d orbitals. That is, this one is d xy, yz or zx. Any of the three orbitals which are in between the axis, we can write as this diagram. And this is the z x square minus y square orbital, and this is the z square orbital. So if we rotate this orbital by 90 degree along the principal axis, that is z axis, if we rotate this orbital, then this plus lobe comes here, this minus comes here, and this plus comes here, this minus comes here. That is, the orbital lobes changes. Here also, if we rotate this by z axis by 90 degree, then this plus lobe comes here, this lobe comes here, this lobe comes here. So here also the sign changes. That is, it should be termed as B. And for this one, if we rotate this along the z axis, then the sign don't change. That is, this is termed as A. But how to differentiate between these orbitals? Because they should have different energy levels. But if we express them as the same term or same naming, then how to differentiate these two? To differentiate them, we rotate the orbitals along x or y axis, which one is favorable, by 180 degrees. If the sign changes, then we use subscript 2, and if the sign don't change, we use subscript 1. There are the orbitals. If we rotate this orbital by x-axis, this is the x-axis. If we rotate this by 180 degree, then this lobe comes here, this lobe comes here. That is, the sign changes. dxy, dyz, dzx, these orbitals are expressed as this diagram. This is dz square, x square minus y square. This is dz square. For this orbital, sign changes. If we rotate this by 180 degree about x or y axis, which one is favorable to us, then we should use subscript 2. That is, the naming of the orbital becomes B2G. Or dx square minus y square. This is, if we rotate this, then the sign don't change. Thus we should use subscript 1. That is, this is named as B1G. And for dz square orbital, this is named as A1G. The G here comes for the J symmetry of the octahedral complexes. This is the energy diagrams of the Z in distorted octahedral geometry. That is, dxy is having lower position, then dxz, yz, then dx square minus y square, then dz square. Now, if we have one electron, then we can have three possible energy levels to where the electron can go. In the first ground state, the energy lives in here, energy houses the B2G orbital. And if we excite this electron, then it can go to EG orbital. If again we excite this electron, then it can go to B1G orbital, and finally it can go to A1G orbital. That is, three possible transitions are there. This B1G, as we have said, that the electron, when we have one electron system, then the electron, when acquires the orbital, that is expressed as the term symbol of the state. Thus, as it is housing in B2G orbital, it should be termed as 2B2G, and similarly the other terms also. This is the ground state, and these three are the excited states. So we have transition from ground state to excited state. Thus, we can have three possible transitions. That is, these three: dxy, xy to orbital to EG orbital, and from x square minus y square up to z square. But this splitting between the T2G orbitals, this is very less compared to this splitting. So these two energy levels will have almost same energy, or we can neglect this lower one also. This is very small energy transition. This is very low energy transition. Thus, we expect two transitions. One is with higher energy level, energy difference, and another is lower energy difference. And this is not. This does not fall within the visible range, so we can neglect this one. So this explains the structure as we have seen earlier. That is the two peaks. That is one peak with another harm. This structure. This stands for the transition from xy orbital to dz square orbital, and this stands for the transition from xy orbital to x square minus y square orbital. Now we will see this in a practical example of these things. We all have detected metal ions in inorganic practicals. A specific example I will show here. It is qualitative analysis of cobalt 2 complexes. We all know that cobalt 2 complexes, many of the cobalt 2 complexes are water soluble. If we have a cobalt 2 plus ion in solution, then if water is added, then this complex is formed, cobalt H2 whole 6 2 plus. And this is when we boil this solution with concentrated HCl, then this complex is formed, cobalt CO Cl whole 4 2 minus. If we treat again this solution with water, then the cobalt H2 whole 6 2 plus is again formed. Cobalt aqua complex is having pale pink color. Cobalt COCl whole 4 is having deep blue color. This is quite evidence from the topics I've discussed, that the tetrahedral complexes will have higher intensity compared to the octahedral complexes. This is octahedral complex. This is a tetrahedral complex. Though chloride ion is lower, though weaker field ligand compared to the water, but as it is present in tetrahedral field, this will have higher intensity compared to the octahedral geometry. And this is have the pale pink color. If we draw the orgel diagram for this complex, then this will look something like this. For cobalt 2 plus is a D7 system. For D7 octahedral, this will have the energy splitting, and when it comes in tetrahedral geometry, that D7 tetrahedral will have this type of electron, this type of energy levels. Thus, we can expect transition from here to here, from here to here, and from here to here. And again also from in octahedral field, we can expect the three transitions. The absorbance peak of the two complexes look like this. The three transitions in the tetrahedral geometry are clearly observable. This one, and this one. There are three peaks corresponding to the three possible transitions. So I am almost at the end of my talk. Now, why to study color chemistry? It helps us detecting some species molecules with naked eyes, as we have done in the qualitative analysis of the radicals, anions or cations. The designing of pigments, color change chemical reaction studies, and spectroscopy studies. And this is all about my talks, and I thank UCG sir, Shobik sir, HG sir, who have taught these things me, and DJ sir for this opportunity to present my lecture. And thank you all.